In this video I'm gonna prove Schwarz Lemma. This will be a little bit unconventional. I'll prove it probably using the maximum modulus principle. That's not unconventional, but maybe I'll go then backwards and prove the maximum modulus principle in another video, and so on. So yeah, we'll see how far backwards I'm gonna go, but let's just start with a proof of Schwarz Lemma. So let's state it. So let f from the unit disk to C be holomorphic with f of the origin equal to be 0, and it should have modulus at most 1 for all C and D, and so that means basically f goes from D to the closure of D, so D is just a set of all complex numbers which have modulus less than 1. And okay, now let's go to the statement. So if f is non-constant, then f of C, the modulus of f of C, is at most the modulus of C for all C in the unit disk, and furthermore f prime of 0, the modulus of f prime at 0 is at most 1. Okay, and furthermore we have that f of C, so the modulus of this is the modulus of C, or the modulus of f prime at 0 is equal to 1 if and only if, let's put brackets around so that it's clear, if and only if f of C is equal to lambda C for some lambda in S1, so with modulus 1. Okay, so let's prove it. So at first we define the function g. So we define it like this. So f of c divided by c, if c is non-zero, and f prime of 0 if c is 0, and of course g now goes from D to the complex numbers. So G is holomorphic. That's first we have the assumption that f of 0 is 0, so we get at first continuity at the origin, and then we know that it's also holomorphic. And now let's take r to be less than 1, and now we apply the maximum modulus principle to G. So I'm maximum modulus principle applied to G, well, G restricted to the disk of radius r around the origin, and here I mean the closed disk, so all complex numbers with modulus at most r. Okay, and then we get for the modulus of g that this is at most, let's say, f of cr divided by cr. So what do I mean by that? So the maximum modulus principle tells us that the maximum can only be at the boundary. So CR has modulus R, and that's why we use this CR. And now, as the maximum is attained at the boundary, we get that this is at most 1 over R, because the modulus of CR is R, and F, where do we have it? The modulus of f of c is at most 1 by assumption. Okay, so that's what we have here. And now we just take let r go to 1, and then we get that the modulus of g is at most 1. And this proves the first two assertions, namely that the modulus of f of c is at most c for all c in D. Well, at first we have it just for all non-zero, but by assumption f of 0 is 0. And here we have the other assertion. Okay, and now let's prove the second part. So let's assume that either the modulus of f of c is equal to the modulus of c, or that the modulus of f prime at 0 is 1. And now we again apply the maximum modulus principle to g. So and what do we get now? Well, we get that g is constant. So let's see why this is the case. So if here we have that this f of c is equal to c, so we have that g, so let me write it down, the modulus of g of c is equal to 1 for some c in the open unit disk. And well, this is also the maximum, which we have this inequality, so that's the maximum, but the maximum could just be attained at the boundary if it was non-constant. So it has to be constant as it's not attained at the boundary. And well, if g is constant, that just means that f of c is equal to lambda c, which is just, let me write it so, f of c is modulus of, f of c is just G of, or let's say here, C naught. So this is G of C naught times C. Okay, so that's the proof. And yeah, I guess in the next video I'll prove the maximum modulus principle, so that you see that that's actually not too hard to prove if one presupposes a little bit more, and maybe then we'll go a little bit more backwards. So thanks for watching and see you next time. Bye.